But I'm just going to go ahead and start with section 4.3. 4.3 is logarithmic functions. All right. Here we go. A logarithmic function with base A is denoted by log base A and is defined as if you have log base A of x is equal to y, then A to the y is equal to x. Okay. So in the log format, or log notation, log base A of x is equal to y. What they're telling you is that A is our base, y is the exponent. In exponential form, this would look like A to the y is equal to x. Notice again, A is our base and y is our exponent. X is the answer. Okay, some examples. Log base 10 of 100 is 2. Remember, the 10 is our base, the 2 is our exponent. So in log format, we say log base 10 of 100 is 2. Because in exponential form, this is 10 to the second equals 100. The base, the exponent. Question. All right. Is this familiar already a little bit, Landon? Okay. Kristen, is this somewhat familiar for you as well? Okay. Good. I just don't want to go too fast if it's unfamiliar. All right. So let's see. If we have log base 3 of 81, okay. So this is saying that 3 to some power has to equal 81. So if I had log base 3 of 81 is equal to some value y, then 3 to the y power would have to equal 81. How do I find the y value here? Well, it's not going to be the third root of 81. Like we can, yeah, we can get there, but it's like we essentially have to, the hard part about this is we essentially have to take 81 and split that into 9 times 9, which would be 3 times 3 times 3 times 3. And we have to recognize that 3 to the y power would be the same as 3 to the 4. So y has to equal 4. All right, similarly, if we have a log base 2 of 1 over 64, and I let that equal some value y, this tells me 2 to some power y has to equal 1 over 64. And I literally have to take 64 and figure out that's 2 times 32, which is 2 times 16, which is 2 times 8. And I know 8 is 2 to the third, so that's 2 to the third, fourth, 5, 6. So 2 to the y would be 1 over 2 to the 6th, or 2 to the y is 2 to the negative 6. So my y value is negative 6. So far, so good? Okay. Alrighty, then let's try log base 5 of 100 is equal to some value y. Then this is saying 5 to what power is equal to 100? If we do 100, that's 10 times 10, which is 5 and 2, 5 and 2. Here's my problem. I don't have just a base of 5, right? So how do I do this one where I don't have 5 to an even power? 5 to the, I don't know, right? Because I've got 5s and 2s. So we need to get some ideas here. There are some common properties of logarithms. Ooh. All right. Oh, trying to turn a page. Come on, page. There we go. Let's look at some common properties of logs. We don't have an answer yet. We've got to look at how we do a few things here. And the graph. And then we'll talk about how to do some of it. Okay. All right, so some common properties of logarithms. Some things we all have to agree on. The log base A of 1 is always going to be 0. So it doesn't matter what the base is, as long as you have the log base A of 1, it will always equal 0. This is because A to any 0 power is always 1. Likewise, if you have the log base A of A, this is going to be 1. In exponential form, this looks like A to the first power is A. Third property. If you have the log base A of any number that is already A to a power, so log base A of A to the x has to equal x. We have to raise A to the x power to get A to the x power. And my favorite, if you have A and you've raised it to the log base A of x power, this is going to give you x. This is an inverse function property. In that if the log base A oh wait, I don't want to say that. Log base A of A to the x is x. then it has to be true that a to the log base a of x has to also equal x. This is true for all real numbers. And for x's greater than 0. All right, questions so far? Excuse me. No, nothing so far. Okay. Okay. Oh, the birdies are so pretty. All right. If I know the log base 5 of 1 is equal to 0, this is true because remember, anything to the 0 power has to equal 1. Base exponent. Oops, sorry, base exponent equals. If I have the log base of 3 to the 8th, this has to equal 8. Remember, 3 to the 8th power has to equal 3 to the 8th power. This is coming from the third property. Log base 7 of 7 has to equal 1 because 7 to the first power has to equal 7. And if I have 12 to the log 12 power of 7, this is going to equal 7. That's the inverse solution. Jeez, people, stop. Can you guys hear the rings or no? Okay. They're super loud on mine. Yeah, my email keeps dinging. It's driving me nuts. Yeah, I live on the north side. There's always motorcycles. There's always people with motorcycles where I'm at. It's just a crazy kind of thing. Right? Okay. So let's try. Let's see. Okay. Let's say I have a log base 4 of some number x, and I know that that's equal to 3. What is the value of x? 4 is the base, right? 3 is the x, and that's got to equal my x. So 4 to the third is indeed 64, right? You can also do this a slightly different way. This was always my favorite way to do this, but log base 4 of x is equal to 3. You can put both of these to the 4th power. Do you see how by my putting the base here, like I'm raising 4 to the log base 4x, and I'm raising 4 to the 3rd power, I get x is 4 to the 3rd, which is 64. You can get this answer either way. The first way uses your definition of a log, and the second way uses that inverse function. If 4 is my base, I'm just going to put each of these on a base of 4, which I can do because if they're equal, then when I raise them to the same power, they're still going to be equal. Questions? Not yet. Okay. Let's do it in a slightly different format. Let's say you had log base x of 6 is equal to 1/2. You can use the definition of a log in that x to the 1/2 power has to equal 6. Now, x to the 1/2 power means we're looking at the square root of x. So now I'm going to square both sides. And x is 36. This uses the definition of the logarithmic function. I can also use the property raising both of these to a power on x. Oops. So that I will have 6 is x to the 1/2 power, or again, 36 is x. Can you see how that works both ways? Okay, good. And they each have their advantages. It's not always one works and one doesn't. So we want to be, we don't even necessarily need to be careful, although a little bit because of the restrictions on the zeros. Right? Okay, where am I on time? All right, I'm fine on time. Okay, graphs are the next thing we're going to look at. Okay. Yes, yes, yes. So if we let f of x equal a to the x in an exponential function, do you remember that in an exponential function, what we were doing previously, there were 3 generic points that I always had us do. We did a -1 with a 1 over a. We did a 0 with a 1. And then we did a 1a. E if it was an exponential, E if it was a natural, A if it was any other base. Right? So E was just a stand-in for the 2.718. So E is just a stand-in for the specific natural number. So if, let's say f of x is equal to 4 to the x power. Then we'd have a -1 and a 1/4, a 0 and a 1, and a 1 with a 4. So we'd have a -1 1/4, 0 1, and a 1/4. And our logarithmic function looked, our exponential function, sorry, looks something like this. And it went all the way up to 16 and it came down. So then what happens is the log base 4 of x is the inverse. So log base 4 of x is going to be the inverse function of this. Remember we said just a few moments ago that these are inverse functions. So that means my points are going to be 1/4, -1. Inverse flips the x and the y. 1 0 and 4 1. Oops, don't want to go away. Very much bleach smile. In order to get the graph of a logarithmic function, it is a reflection of the exponential function over the line y equals x. It's a reflection of the exponential function Notice that this one has a vertical asymptote at x equals 0, and that its most basic form, as x approaches 0 from the right, y goes to negative infinity, and as x approaches infinity, y goes to infinity. Questions about lovely graph? Nothing yet? I haven't given you the hard stuff, so we're good. All right, let's try a couple. Okay. Boop, boop. All right. The transformations can be used just as they were before. So we want to graph using transformations. Let's try a couple of these guys. Okay. Let's see. Let's let f of x be equal to log base 2 of x minus 4. All right. So if we just start with a base function of log base 2 of x. I don't know if you can see that, just barely maybe. There are 3 points that I can use, inverse from before. 1/2, -1, 0, I'm sorry, 1, 0, there we go. And then 2, 1. Okay. So I know that my log graph is going to look something like this in the base. Questions on how I got those 3 so quickly? Okay. All right, so how I did it quickly. Here we go. If this was 2 to the x power, can you guys even see that? I don't even know if you can see it. Okay, is that a little bit better? Get the light off. Okay, if we had 2 to the x power, then I could use the 3 points that we did last week, right? I'd have a -1, 1/2. 2 to the -1 power is 1/2. If I let x be 0, this would be a 1. And if I let x be a 1, then that would be 2. Are we okay with those three? Yeah, I'm using logs and exponential functions are inverses of each other, right? Okay, so as inverses, no, I didn't. Okay. I gotta get rid of this. Okay. Here we go. Log base 2 of some value x is the inverse of 2 to the x power. We graphed 2 to the x power last week. So if we start with what we know, graphing 2 to the x power, we get the 3 points. We put -1 in for x, we'd have 2 to the -1 power, which is 1/2. If we put 0 in for x, we would have 2 to the 0 power. That's a 1. If we put a +1 in for x, we'd have 2 to the first power. That's 2. Are we okay with that? Landon, you okay with that piece? Good. So then log base 2 of x would be the points 1/2, -1, 1, 0, and 2, 1. Okay. Now you know how I got this graph. Yes? All right. Now, what's the -4 inside there going to do to this graph? It's going to move it right forward. We got it. We got it. So now I need to move all of these points right forward. 1, 2, 3, 4, 4, 4. There we go. Okay, can we try another one? We can try another one. Okay. Love the enthusiasm, Christine. Love the enthusiasm. All right. I know, I know, I know. Okay, so let's try y is equal to 2 minus log base 3 of x. Okay, so I'm going to start with my base function here. Log base 3 of x is the inverse of 3 to the x. If I go back to what we did last week and I graph 3 to the x, That's going to be a -1 and a 1/3, a 0 and a 1, and a 3 and a 1. Oh, 1, 3. Sorry, I did it backwards. Trying to do 2 steps at once. That means that the log base 3 of x is going to use the points 1/3, -1, 1, 0, and there we go, 3, 1. And you can see what this base function is going to look like. Okay, now, using our transformations, what is that negative going to do to my log base 3 of x? That's going to reflect it over the x-axis, meaning my new points would be there, there, and there. And what's that 2 going to do? Meaning I'm going to be there, there, and there. Alrighty? Seeing how the transformations work again. Yes? Okay. Woohoo! All right. Couple more pieces if I don't know how much I can get there. Okay. Two pieces I want to do kind of quick here. The first is the common log, and the second is the natural log. Both of these are on your calculator. They are the only ones that are on your calculator. The common log is base 10. And is assumed when the base is missing. So if you're just looking at something and it says log x, the assumption is that we mean log base 10 of x. Base 10. The one's just really close. Natural log is base e. And is denoted by ln, or log natural. If you see ln x, either in cursive or sometimes in print, this means log base e of x, also on your calculator. I'll shift it. I want to try it. Okay. You got a calculator handy? Okay. Awesome. All right. So if we are asked to evaluate, so here's what you may see. You may see ln 5. Now, on your calculator, you want to find ln and log. And on this calculator, they're both in the first column. Log is the second key down, ln is the third key down. And if I need to find the natural log of 5, I'm just going to hit ln and 5. And it lets me know that that is 1.609. And if I'm asked to find the log of the square root of 2 plus 4, I'm just going to hit log square root of 2 plus 4. To get a 0.734-ish. And if they give me something like a log base 5 of 7, you cannot do this right now. We'll work on it later, but right now the only ones that you can do are LNs and log base 10s. Because that's all you have in your current toolkit. So please don't think that you could do a log base 5 of 7 right now. You can figure out that 5 to some power y is going to be 7, but I don't know that you could work that back to figure out what y has to be. Other than to say it has to be between 1 and 2, right? Because 5 to the first would be 5, and 5 squared would be 25, and I've got an answer of 7. So it's got to be between 1 and 2. But that's really all you could say about y right now. We'll work on how to do those by Wednesday. We'll have that one. All right? We still need to go over a couple of things in this section. So you should be good up until domain stuff. We'll do some domain stuff a little bit later in this. And there might be some applications where you're just not confident yet. We've gone over everything you need to, but you may just not quite be confident. But yeah, that's what we've got started for today. And we'll do some examples tomorrow, and we'll talk about some domain things. Absolutely. Yeah. Okay. Yes. Oh, it would be 3. If your x is 10 to the third, then log base 10 of x, remember that's log base 10 of x, has to be the exponent. What's your exponent for that first one? Good. That's what they want in that box. Yep. They're just flipping it between formats there. That's all they're doing. You're welcome. You're welcome. All they're doing is flipping between formats. Yeah. Nope. Yep. Nope. You were doing too much. You're welcome. Landon, anything from you before we go? Okay. All right, guys. Thank you. Whoops. Did I just zoom out? Are you still there? Okay. Sorry, I closed out a screen and I thought everybody went away. You didn't all go away. It's okay. All right. We're good for today then.